part of ICECE 2022. Today, I would like to present our work on modeling second order anisotropy of monodomain magnet body. Co-author of this paper is Dr. ICECE. This is just an overview of our work where we model the magnetic field layer of a magnetic terminal junction using the ICECE software. Then we added the extra HKB parameter for the second order anisotropy. And lastly, we simulate our model and observe the magnetization dynamics of the magnet. Outline of today's presentation is a brief introduction to the magnetic random access memory and magnetic tunnel junction. Then, to understand the magnetization dynamics, I will be talking about the LG equation. Then I will talk about how we model the magnet body and the simulation result. And lastly, we will talk about the summary and future scope. So, the motivation behind our work is to create a realistic magnet model that can help us to build the future magnet random access memory or MRAM. This MRAM is the future of the memory storage, which has many advantages over conventional charge-based memories, such as non-conductivity, faster read-and-write cycle, energy efficient, and viability. Now, to build an MRAM, we need MTJ or magnetic tunnel junction. MTJ works using the spin characteristics of the electron. It has two layers. One is free layer and another is spin layer. These layers are separated by an insulator. By applying external voltage or current, we can reverse the magnetization direction of the free layer, and by reversing this direction, we can have two states in a magnetic tunnel junction. They are anti-parallel state and parallel state, and these two states actually define the 0 and 1 bit for the magnetic tunnel junction. Now to understand how to reverse the magnetization direction, we have to look at the LG equation. This equation gives us an insight how we can create damping and reverse the magnetization direction. In this equation, the torques originates from the various anisotropy fields that affects the magnetic body. Now, ignoring all the external effects, there are three types of anisotropy field in a magnet. They are first order anisotropy field, second order anisotropy field, and the easy pair anisotropy field. This equation actually gives us the potential energy that originates due to the anisotropy fields. In this equation, the HQ1 and HQ2 is the first and second order anisotropy fields. HP is the equivalent anisotropy field. MS is the saturation magnetization, and theta and phi are the polar coordinates of the magnetization direction. Now, what is actual anisotropy? Anisotropy actually describes that properties of magnet are unequal in different directions, and it originates from various sources such as magnetic crystal anisotropy, shape anisotropy, and surface and interface anisotropy. Now, why do we need to consider the second order anisotropy? Because previously, most of the model they didn't only use the first order anisotropy because the second order value was not that much comparable to first order. But due to the smaller difference sizes, the second order anisotropy value now gets much more comparable to the first order anisotropy value. And also due to the recent evolution in voltage controlled magnetic anisotropy, where it is possible to tune the interface anisotropy of the magnet. So in that case, the second order value gets much more importance compared to the first order. Also, for some computation model, we actually need low barrier magnet. And in this low barrier magnet, the first order value gets close to 0. So to understand the magnetization of this low barrier magnet, we actually have to consider the second order anisotropy value. And lastly, in some studies, it has been said that for some fixed first order and second order anisotropy value, there can be an easy constant, and this state can actually help us to reducing the writing density of the magnetic tunnel junction. So for this reason, we need a model that incorporates the second order anisotropy effect. So we want to solve this LG equation in SPICE instead of MATLAB. But you may ask why SPICE? Because in SPICE we can create circuit compatible model for simulation. Also, we can add real-life noise to the SPICE model using the resistor with random current source. So, but actually SPICE is a circuit solver. It has components like capacitor, resistor, voltage source, and current source. It's not a differential equation solver. So our work is to implement a differential equation by SPICE inbuilt components. To do this, first we take the LG equation in forms of torques. These torques originate from the various anisotropy field that the magnet experiences. Then I converted the Cartesian equation into spherical coordinates using the mathematical software. Lastly, we map the LG equation to the capacitor equation. If we look at the capacitor equation, the differential part of the capacitor equation can be mapped as the part of the energy equation. Also, summation of torques can be think as a summation of current source in the capacitor equation. And other parameters such as HP, H external, Hs can be mapped as a voltage across resistance. So this is the circuit model for the theta coordinate where each torque is represented by the current sources. Here PU2 is the second order Anisotropy effect that I added to the existing model. And this is my circuit model for the pi coordinates. In the SPICE coding, I give the magnet parameters such as the thickness, diameter, damping coefficient, etc. as input. And in the output, we get the magnetization direction. Our code has many features such as we can transform this magnet body into in-plane magnetic anisotropy or perpendicular magnetic anisotropy. Also, our model can analyze both low barrier and high barrier magnet. It considers up to second order anisotropy level. And also, we included the thermal noise in the energy equation. So, to understand the magnet performance, we have to evaluate some parameters. In our case, we simulate for two types of effect. They are critical current and critical field. These values are the minimum current and field that is required for the magnetization switching in a magnetic transition free layer. Now, if we look at the simulation result, here I have simulated for both 40 kVt and 60 kVt barrier magnet. First, we benchmark our model with 0 second order anisotropy value and compare it with the theoretical result that is previously available in the studies. Then I added the second order anisotropy value and observe the output. You can see that as the second order anisotropy value is increasing, the critical current and critical field required for switching is also increasing. And for 0 second order value, our result actually matches with the theoretical result. So it is safe to say that while we are going to design a magnet, we have to consider the second order value of that magnet to actually define the minimum switching field and current required for that magnet. If we look at the critical field and current graph, we can see that both of the current and field is increasing as the second order value is increasing. This table actually shows the percent increment of the critical field and critical current from the 0 second order anisotropy. And also, you can see that the second order anisotropy emits much more on the low barrier magnet, but it actually has less effect on the magnetic field. So in summary, we modeled the LHC equation using the SPICE software. Then we added the extra second order anisotropy to the existing model. We simulated for critical current and critical field, and we found that the increase in the second order anisotropy actually increased the critical current and critical field. In future, we want to investigate the switching time variation for various types of second order anisotropy value. And also we want to find a suitable value for first order and second order anisotropy to find the easy constant. The code is actually available after request to the author, or you can scan the QR code to find our SPICE code. So thank you.